we've reached the point in the course where we need to talk about RTL design. RTL stands for Register Transfer Level, and it's a level of abstraction that helps us more effectively design certain digital circuits. So let's talk about this in a little more detail. So far in the course, we've talked about various levels of abstraction. By that I mean we started with transistors and we figured out how we can connect transistors in certain configurations to make the next level, which was logic gates. From there, with logic gates, we were able to build other building block kind of circuits. For example, we had adders and multiplexers and encoders, and we even cross-coupled NOR gates to get memory elements. And from there, we got flip-flops and registers. These form the foundational building block levels. Next is the RTL level, register transfer level. This is where we are. This is a place where a lot of digital design work happens. So how do we complete a digital system design at the RTL level? We have the building blocks. Now we need to organize those into some methodology that helps us make systematic progress towards solved circuits that accomplish things with the design that we want to have. I should let you know, though, in practice, experienced hardware designers work directly, in many cases, directly in HDL, things like Verilog or VHDL. They've internalized this idea of separation of data and control. They've internalized ideas of RTL structures. And so they don't necessarily go through this same sort of detailed approach. They are able to jump straight into the HDL. And they have a mental model for making this work. So when you're learning digital design, I think it's important to have a technique to understand how, when you write things in Verilog, for example, to describe hardware, you have a mental model for what it's doing, how that hardware gets realized. So that's what we're working on. And because it's not an industry standard, because people can jump straight into HDL, different textbooks have different notations and terminology for how this process would go. There's a few textbooks out there that talk about finite state machines, FSM, and they put a D at the end for data path. There's some other textbooks that use this idea called ASM charts, algorithmic state machine charts, where they look a lot like flowchart diagrams, and the information about how registers have data transferred in them show up within those blocks of the flowchart. The Zybooks approach has a high-level state machine kind of terminology, but these are basically the same ideas, the same notions that talk about describing an algorithm and then systematically decomposing this into hardware. So I feel like the most common terminology is this finite state machine with a data path, and so that's what we're going to use in this course. Okay, so to start, I'm going to show you a very simple finite state machine with a data path. So this is the normal finite state machine where I have bubbles indicating states. I have a scalar input B for button, if you will, and we can traverse different transitions and go through the finite state machine. Where it becomes having registers and transfers within those registers is to the side here in blue. I've highlighted where I have this T register. Think of T as maybe an 8-bit register, and you can load values of T that come from the different states. Okay, so once you have the finite state machine with the data path, then you can come up with the data path that supports that. That's the general idea. Okay, so a finite state machine with data path, FSMD, the whole idea is this captures the algorithm or the process that you're trying to accomplish with the state machine design. It's all there in a single diagram, and from there you can come up with the hardware realization in a systematic way. Okay, so an important concept is that the states, each of these individual states in this example, contain the register transfer operations. Sometimes the transition paths might actually depend on external inputs, like I've shown here, or it might depend on certain data conditions that happen within the data path. So that's a possibility as well. So the key insight is that the FSMD mixes data and control together so you can get an idea of how everything is supposed to work together. But from there, you need to separate the control from the data to come up with a systematic way of implementing the hardware. So that's a key concept. Every RTL system decomposes into two cooperating parts. You have a controller that I view as sort of a regular finite state machine, and then the data path that the controller actually runs. Okay, so these things work together to support each other. The data path supports the computation. The controller sequences what happens within the data path and makes things actually happen. All right, so here's the way I want you to think of the process that we're going to go through. We're going to work through several examples of this, and then we're going to relate it back to Verilog and HDL approaches. The first is we help put together our ideas for design with an FSMD, where we have an idea of how the architecture should go, how the algorithm should go. We come up with ideas and we represent that in a single diagram. From there, you can build out a data path that will support the FSMD. And then once you have that, because you know the data path and you know what is supposed to happen with the FSMD, you can build a more traditional finite state machine that can be implemented in hardware that will actually run the data path. And by the time you put those two things together, you have the full circuit. Okay, so that's where we're heading in this section of the book. It's a fun process, I think. It's the process that lets you actually do some pretty cool little designs to help you learn digital logic.